This talk covers principally work in Postgres 18, but also work in Postgres 17, which is closely related. Here's an overview of the talk. So it's 4 different sections. I'm going to give you an opportunity to ask questions every time you see this overview again. So I'll go through what each section will discuss briefly. First, I'm going to give you a high-level overview of the feature, why you care, what the benefits are, and some idea about the internals. I'm next going to discuss some of the core design philosophy, particularly with respect to the optimizer and how the feature pushes off as many decisions as possible to runtime, decisions as to skipping. Then I'll talk about work also in Postgres 18 from another group of contributors. This work in the optimizer is related to the skip scan work in that it makes it more useful in more scenarios, particularly those involving ORs. And then finally, I'll move on to the more speculative section of the talk where I'm discussing the, what would you say, future improvements that can be seen more or less as an enhanced version of the stuff we're talking about in section 3 with ORs applied to more complicated cases and not just simple lists of where foo equals 1 or foo equals 2 or similar such constructs. So with that, I will begin. I'm going to ask questions. I'm going to ask if there's questions at this point because I don't think I've been. Okay, so what is skip scan? Skip scan is an optimization where it's possible with a composite or multi-column B-tree index to use that index in more scenarios than was previously possible. Essentially, this works by treating a composite index as a series of logical subindexes, one per distinct value in the leading omitted prefix column. So this is feasible in cases where there's not too many distinct values in that prefix column. In other words, in order for this to be useful, there can't be too many logical subindexes. Now I'll show you a picture. This is from a paper that influenced my work. It's a 1995 paper about multidimensional access. This particular example, if you imagine an SQL statement with dimension 3 equals 2, and then this is a composite index on dimension 1, dimension 2, dimension 3, and in this sort of toy example, each column only has 3 distinct values. So the shaded areas indicate the parts of the index we'll have to read. All the rest of the index is irrelevant to the scan, and therefore we don't have to read those parts of the index at all. Here there's like 27 distinct combinations of dimension 1, dimension 2, dimension 3. That is 3 multiplied by 3 multiplied by 3. So when we get to these unshaded areas, we can skip over that part of the index and pick up at the next shaded area. So this is obviously a very simplified example, but in the real world, what we would actually be doing is, this is accessing about 1/3 of the index rather than doing a full index scan. Real world examples would typically be some small fraction of the total index would actually need to be read, usually. So this isn't a particularly compelling case for skip scan. It's just a simplified sort of representation of how it works. It does need to go from the root again, but only to get to jump to the next part of the index that might have relevant data. So it's going to do that. The overall effect is that those parts of the index that are definitely irrelevant, usually most of it, won't need to be scanned. Traditionally, a full index scan could be used, but it would be very inefficient. It would have to scan the entire index. And that usually meant that it wasn't a viable strategy, that we would have to do a sequential scan. Right, it would just not choose it because it just didn't make sense given how the access method worked on prior versions. So there are benefits for users that I've covered already somewhat. I think this is important for robust performance. That is, it's important when we have unexpected new deployments. Queries can perhaps get by with available indexes with acceptable performance. I think it's also possibly quite compelling in scenarios where it allows users to get by with fewer indexes. If an index can support more queries with reasonable efficiency, we don't need to have too many duplicate or partially duplicated indexes where we have every permutation of the same columns. There's also, this is more of a speculative slide. I would also point out that there are scenarios in which, when designing the perfect index for an important query, we legitimately need to make a choice. Suppose you have a query with some mixture of range inequality conditions, so inequalities, possibly a date column with between this date and that date, plus some other selective index column. You could imagine you would want to ideally have the column order match the order by from the query in order that you can terminate the scan early with an order by limit. You would want that, but then it's not obvious that you can get that benefit. You might also prefer to put the more selective column first instead. That would mean that you would always have to read all the data before being able to return one row, and then you'd have to do a sort. It's unclear in the general case which to prefer. And this is sort of a fraught process because you have to worry about the worst case much more than the average. What if occasionally the scan returns 0 rows? Then with the order by version of the index where you prioritize that, where you make the index column order match the order by, it's going to have to scan a great deal of data. So my speculation here is that with skip scan, the risk of that happening, at least in some cases, can be significantly ameliorated, thus favoring the order by strategy more than would have been feasible before. I have to admit that I'm not sure how practically relevant that point is, but it's worth considering that it could make a great deal of difference in a scenario such as this. If anyone is aware of cases like this, they should let me know about it. So here's an actual simple worked example. You could run this yourself. I'm creating a table. I'm populating the table with 10 distinct values in the leading column A. The column B has many distinct values. And a query like this, select star from table where B equals 5,000, is able to use skip scan internally. Here, this is shown. This is obviously a syntax that I made up. This is not a real array literal, but conceptually, it's very much doing something close to that. It's reusing the same machinery internally that we would use for an actual real array such as this. It would also return null matches, which we have to because, I mean, this isn't really here. This is all made up. We have to return nulls, which is not something that we'll ever do if you're actually using this syntax. So here's explain analyze for this. It happens to be an index-only scan. Here we see there's 10 distinct values in the index, but we get index searches 12, and that's because we need two index searches we need the first index search to discover what the lowest integer value in the index is. We don't know that ahead of time. It happens to be 1, but we don't technically know that until we look. And then we iteratively go through the index where A equals 1, B equals 5,000, where A equals 2, B equals 5,000, etc. And then we get through all of the actual existing rows, returning a total of 10. And then we try where A equals 11 and B equals 5,000, which doesn't exist in the index. So what happens then is we just find the rightmost leaf page doesn't have any matches, then we're done with the entire top-level scan. So, as I said, very much reusing the same machinery used for in previous releases, well, really Postgres 17 for scale array ops, which is how we internally refer to anything that uses these sorts of constructs, like where A in 1, 2, 3, or where A equals any 1, 2, 3. Postgres 17, following work from me on that release, is much smarter about whether or not we require an independent index search for each distinct value in an array. Here we see where suppose you have where A in 1, 2, 3, it's quite likely in general that those values would be close together on the same index leaf page. So for that sort of query, we would expect to see only one index search. However, this somewhat similar where A equals 10,000, 20,000, 30,000 would be much more likely that they would be physically spread apart. So naturally, we would have to do it the same way as we would in Postgres 16. We'd have to do one index search per distinct value there. It all depends on the physical index characteristics. We're on the fly determining how we want to do this stuff. We're finding the most efficient way to do it at runtime. It's adaptive in that sense. Okay, so I'm actually showing this here. Now, we only require 10 index searches here because we know from the predicate exactly what we require. So that's fairly similar, but not quite, because we don't have those 2 extra index searches as we did with the skip scan. This is an index-only scan that uses a range skip array. So this is using skip scan. Even though the column on A hasn't been omitted, it's using between instead, which is basically equivalent to using these inequalities that you see in the index condition. That also gets 10 index searches, because we know there that the relevant values are 1 through 10. And we're doing almost exactly the same thing as the scale array op example. That's because internally, the way we represent these two things is basically near identical. Conceptually, we're using something called a skip array, which, like a conventional scale array op array, is something that we, as we scan the index, we advance our current position in the array, and if we find that we are at the end of matches for that element, we advance to the next element. This needs to work in a way that considers the arrays as a group. For example, if we reach the end of an array that's the low order array on column B or the column C, that needs to roll over and increment the value in column B, which perhaps could in turn need to roll over and then increment the other array on column A. It all depends, of course. So they need to work as one group, and having this generalized notion of an array that can maybe a skip array, maybe a scale array op array, quite useful architecturally because it confines knowledge of the distinction between these two things to the lowest level code. So I'm going to show you an example here. This is a fancy kind of complicated example, which is directly lifted from the source material, the MDAM paper. This is combining many of these different constructs together at the same time, and everything works just as well as it possibly could. So here, we've got a composite index on department, date, item class, store. If you look at the predicate, the department column is wholly omitted. Next, we have a date, and it's a range of dates. It's 30 dates. After that, we have item class, and after that, we have store. And these are obviously using traditional arrays. And again, these need to work together as a unit. So the next page shows the actual physical accesses we're doing. There's 9,002 distinct index searches here, as indicated by explain analyze. That's because of the, you can work it out here. There's 1,800 rows returned. This is pretty synthetic data, so it's 100 departments, 30 days, 3 item classes, 2 stores. Now, it just so happens that the item class and store, the stores 200 and 250 tend to be located close by on the same index leaf page. So we only need half the number that you would expect, perhaps, of index searches, plus another 2, because we still need to do the thing for the department column where we're getting the lowest department, and then we're searching for something that doesn't exist. Like in this case, it will be department equals 101. There's no 101, so it fails to find anything, and then the scan's done. So it's reducing this very complicated, messy, big index scan to a series of primitive index scans, index searches, that are sort of pretending to be one continuous index search, but in fact are not. Okay, I will take questions on any of that you might have. Yes? How do you find the value of the range of the distinct? Mm-hmm. So there is a infrastructure called skip support. If you're using integers, you can just get the next integer value by adding 1 to it. The same is true if you're using dates. In fact, all of the examples I'm using today happen to work that way. For something like text, we can't do that because you can't add 1 to a text literal, right? So we have to use sentinel values instead. But you can think of it as the sentinel value is representing the value from the original value plus infinitesimal. You could think of it like that. So that's just interpreted as find the next one in the index. But basically everything works the same way. The advantage of having skip support is if we're guessing the next thing in the index, we start from 1, we guess the next thing in the index is 2, we save ourselves an extra index search to determine what the next value is if we guess right. If we guess the value after 1 is 2 correctly, then we don't have to do it like a next key search from 1 to get to 2. We save ourselves some work. Of course, that gamble might not pay off, but that doesn't really matter because then it hasn't really cost us anything. We had to do that anyway, right? The effort to do that, the failed effort is pretty much equivalent to just doing it the other way anyway. Exactly, yes. I think it's very common for integers and dates to be contiguous, so it doesn't... Well, there's no real trade-off because either you're right about the next value after 1 being 2 or you're not. If you're right, then you win slightly because you don't have to do another index search to find the first value of the index that's greater than 1. Well, the way that it works is we don't know ahead of time exactly how many index searches we'll have. It's all dynamic. It's all on the fly, and we're doing that. We're deciding all that on the basis of physical index characteristics. So there's no telling if it could be that. Again, this is synthetic data. It's not very realistic. Everything's very uniform, but there could be clustering of values in one area where we would want to read everything in one go. Even during the same index scan, we could later find that things are spaced apart by quite a bit, in which case we ought to do that. So we could change our mind and change it back, and I go on about this a little bit later. Yep. Yes. Is
that actually needed? It sounds like...
Oh, it is needed because you don't know what's in the index.
Sure, but I mean, when you're traversing an index to find the first one, you could just as well check if it also is like matches 5,000 if you go a bit further, right?
Right. If it happened to be that you had the lowest possible integer value in the index, if you inserted negative 2.1 billion whatever, then you wouldn't need an extra. That would actually just happen. But in this case, at least, the actual lowest is 1, not negative 2.1 billion whatever. So it doesn't. That didn't work there because the physical data, the physical index characteristics did not allow it. But it could be that it's not particularly likely, but it could happen that way, in which case you wouldn't need to.
Sure, but I mean, while you're traversing the index, you realize sort of that it's 1.
Yes, exactly. Yeah.
So then if you go like, instead of returning that straight from the index search, you go like one step further, can't you say like, it's 1, that's the lowest, and it has 5,000.
Right.
And you only need 1 index search.
Well, it would. I suppose also that you had. I mean, that's not particularly likely here because the initial search will probably land on a leftmost leaf page that contains 1 up until several hundred. It's unlikely that I deliberately constructed the example. It's unlikely that the value b equals 5, a equals 1, b equals 5,000 would be on the first leftmost leaf page. What actually happened here, in fact, because this is a real world example, was it was probably a few leaf pages after that. So it does make sense to do another index search just to, but again, that might not always happen. It's happening here, and that is probably fairly much typical. You tend to see like 2 extra ones for the minimum and the maximum, as we've seen so far in that original example and the more complicated. Okay, I need to get through this because I'm running out of time quickly. Okay. Architectural goals. It's really hard to cost this stuff. Can somebody give me a drink of water? I'm getting a little bit... It's really hard to cost this stuff in the optimizer, and the actual approach taken is to not, within the optimizer that is to not invent a new distinct type of index path, but rather to reuse the existing ones, accounting for the fact that we can skip in the costing of those index paths. Index path is the representation of an index scan from the point of view of the optimizer. So we're totally reusing those. The only changes the optimizer required was to the costing of the index scans. Thanks. This is nothing new. Like, you could get a full index scan in previous versions, even if you've omitted the prefix column or anything like that. It's just that it would usually be very slow and impractical. You would just be better off with a sequential scan. So because I'm not inventing a new type of index optimizer path, it was necessary for me to preserve all of these existing behaviors that worked. So long story short, all these things continue to work with the new code by reusing Postgres 17 code. So in short, the approach we're taking is dynamic and adaptive. And this necessitates code that makes it okay when it just so happens that we have an index that really maybe should have used a traditional full index scan. Sometimes that may just be the fastest available plan. It might not be fastest, it might not be particularly fast, but it could nevertheless be the fastest available plan overall. Typically, this happens with an index-only scan. So we might not be able to skip at all. We're always open to the possibility of skipping, and we need to not pay too high a penalty for making that possible, even when it doesn't actually make sense. Also worth noting, you can have skew. So even when, broadly speaking, skipping is the right thing to do, there could be large individual subsets of the index where skipping is hopeless. So we would need this sort of thing to deal with that anyway. This is a quote from a researcher who's fairly influential in my work, Guts Grefa. Here he was mentioned in the keynote this morning. Here he is talking about the difficulty with costing a skip scan and argues for a dynamic runtime strategy. So I think probably I owe something to him and his influence here. Okay, so I'll also point out that there's more than one type of skipping involved here. It's not documented or anything, but by having these skip arrays, by teaching the B-Tree code, hey, you could treat this as a kind of a multidimensional structure. Even when we're not able to skip in the way that you would hope, we can still skip within a page by applying that same concept, which turns out makes quite a large difference. In fact, in the example you saw earlier, you'll recall how an an individual store, they were on the same page, but they were close together, but they weren't that close together. It was 200 and 250, right? So we could skip within a page by applying the same principle. It's surprising in general, in fact, how important the cost of predicate evaluation is. So even in cases where we're doing what you would think would be way too much skipping, we seem to come out ahead all the same just by avoiding the overhead of predicate evaluation. So if we're skipping within a page, say, we're not doing anything with most of the individual index tuples on that page. We're saving the effort of predicate evaluation. Even if we're not actually skipping, that's giving us quite a nice boost. This is not necessarily all that important for you as a user, but the point is, this argues, I think, for the design that makes every index scan that's potentially eligible to skip actually capable of skipping, and not making a cost-based choice as to skipping, not having a distinct type of path that embodies the idea of skipping as a distinct thing that we must make a choice, an upfront, inflexible choice around. So it also helps with cases where we can do no skipping, but we can avoid evaluating an earlier key. So this is an example of a query that benefits in that way. It's not capable of skipping within a page even, but we can avoid evaluating the scan key on A, the lower and upper bound, completely in this case. And this was like, I think, about 50% faster. So even though we don't actually skip at all, even within a page here, it's still quite significantly faster. And again, skew can always occur. And by being prepared for all of these different eventualities, being prepared for the case where skipping doesn't help, and being prepared for the case where skipping helps a lot, and being prepared to change our mind at a moment's notice, the system is more robust. The system is better able to handle skew, which is probably going to be naturally occurring anyway, even in cases where skip scan actually overall is absolutely the best choice. So I think it's pretty obvious that in real world data, you tend to get these sorts of, skew is very common. I think it's pretty much self-evident that there's no reason why an index scan has to be just one particular thing. It could be a lot of skipping, it could be a lot of not skipping, etc. Just because that's how the data happen to come out for whatever reason, whatever real world reason. So at this point, I'll once again ask if anybody has any questions. Any of that? No? Okay. All right. I'm going to now discuss, as I briefly touched upon already, tangentially related work. Actually, one of the authors is in the audience here, on the optimizer for Postgres 18, which has been taught to transform OR clauses into the representation that we can use in the index code, that is the scale array op thing. So this makes it possible to use all this stuff in many more cases than would otherwise be possible. As I mentioned, Elena Rybakina, she's right there, Alexander Korotkov and others. That's just a number of commits in this area. The basic work was the transformation of an OR clause into a scale array op, and then there's also cases involving joins. So you can do a join that has an OR condition in it, and you'll get a nested loop join, and the inner index scan will be able to push down the multiple distinct elements as an array. So there are scenarios which that could be very useful if you have an OR and a join condition. They can make quite a big difference. So here's diff output from one of those commits. I don't know if you can see that very clearly. What it's showing here is this query, which is, speaking of, we had DeWitt this morning. This is from his Wisconsin benchmark, the same test data. We use it for the regression tests. This is, he alluded to or referenced it earlier in his keynote, saying that's why he got sued, or they tried to get him fired, or whatever it was. That's just kind of an aside. So here, before we were getting, as you can see, this is the old diff output, or the old test result output, which is removed by this diff. We have 3 distinct index scans, all against the same index, for each of the 3 distinct values you see in the where clause. Now we just have one index scan, with, of course, array syntax indicating the 3 values that are in the predicate. So this is useful because probably the most obvious reason why this is helpful is because there are inherent costs in having 3 executor nodes rather than 1. But also, quite obviously, now that you're pushing down the information to the index scan, you automatically benefit from all the stuff that I added to Postgres 17. You're able to potentially read everything in one go on the same one-leaf page. You might also have to do 3 different index searches. Of course, it depends on the distribution of data. It may not be possible, but at least this way, you are always open to the possibility of just reading all relevant data from the array in one go, or at least doing that for partial subsets of the array. And that is just an automatic consequence of using the scale array op representation internally. But that's also fairly obvious, though. But what is a little bit less obvious is that here we see a similar query to the one I showed you. I've added a limit 2 here. And so because of that, we're only getting 2 rows returned instead of, I think, 4. And we're avoiding heap access, we're not just gaining efficiencies in the index access method, although we're also, by virtue of the fact that we're using a plain index scan, which we can say reliably returns the tuples in index order, we only have to read as many heap pages as required to satisfy that limit 2, then the scan returns. So we're saving heap accesses here in addition to the more obvious benefit. So if you think about it, a bitmap index scan is just generating a bitmap with a representation of all the TIDs that match, which doesn't preserve the sort order. It's in the most convenient order for the bitmap heap scan, which will access those matching rows, but it's quite inconvenient from the point of view of the sort order of the index. We've lost all that information. Here we're preserving it, and potentially that's making all the difference. Okay. Also, if we change it to get just the index columns, now we're getting an index-only scan, which is better still, because we can't do an index-only scan if we are going to do, there's no such thing as a bitmap index scan that doesn't have a bitmap heap scan. So we have this previously we had this undesirable consequence of using a bitmap OR for any OR condition. It implied that we wouldn't be able to do an index-only scan at all, which seems illogical to me. So anyway, by doing this analysis, we're able to have ordered index scans, we're able to use index-only scans. Obviously, that's potentially very useful. It all depends on the particular query, but that could make all the difference. At this point, I'm going to move on to talking about the more speculative aspects of this work, how I think this can be further generalized to work with more advanced, more complicated OR constructs. So it's basically taking the same general idea and pushing it much further. At this point, I will give you another opportunity to ask questions, if there are any. No? Okay. So the MDAM paper finishes by discussing these complex scenarios with complicated, somewhat contradictory predicates with ORs, and describes a way to reduce them to a series of index searches that basically do have the same benefits as those that I've already described for the work in 18. You get a an index scan that preserves the index order. That can make the crucial difference. Or maybe you get an index-only scan where you couldn't before, which could make a huge difference. Like making the same basic trick I've already described work in more complicated cases is what I'm going to talk about now. One important aspect of this is that in order for any of this to be correct, so when we're using a bitmap index scan with bitmap heap scan, one of the things we get for free, if you like, is duplicate elimination. It's only possible to set a bit in the bitmap once. If, for example, there is a bitmap OR with two bitmap index scans and they both return the same TID, it doesn't affect the correctness of the query. We'll still in any case only return the TID once, the correct number of times, because we won't. The attempt to set the bit a second time will just be a no-op effectively. So we're getting that for free. It's something that's easy to miss. It's kind of obvious when you point it out like that, but like you're getting duplicate elimination for free with this bitmap OR approach, which is actually pretty nice because it's so general, but is also not so great because it implies that we have all these downsides that we would really rather avoid. We can't do index-only scans effectively. We can't terminate a scan early with an order limit by, et cetera, et cetera. So the picture in Postgres 18 is kind of mixed. Here is an example using the same table showed earlier, where we have an OR with a range of dates. Now, suppose I had written this where department between 1 and 8. Then we would have just gotten a simple range skip scan, and it would have shown 16 index searches, and that would have been perfect in the sense that it wouldn't have had any of those disadvantages. It could have been an index-only scan. It could have been a plain index scan, etc. But that's not what I wrote. I wrote this slightly similar OR thing here. Now, we're not supposed to return to department 4. That's just how the query is specified, right? So we certainly can't use a simple index scan that uses skip scan internally because that would return rows with department equals 4, which would be wrong. So what do we actually get? We get this this plan here, which is a bitmap OR. Now, there's some things that are pretty good about this. Like, this is not all bad news, because we are using each of these individual bitmap index scans is using skip scan. This is evidenced by, well, before we can sort of work it out, we have 2 dates, and this one has 3 distinct departments. So that's 2 by 3 is 6, and similarly, 2 by 4 is 8. So this kind of makes sense. Like, this is not too bad. It would be way, way slower on an earlier version. I'm not going to show that, but you can take my word for it. But nevertheless, it's a bit unsatisfying because actually, this is our main problem that remains. It's great that the index scan, the index access is almost as efficient as it could be, but we still have this problem with the heap accesses. Could we get an index-only scan? We are in fact capable, this is pretty much just summarizing what I said, we are in fact capable of getting an index-only scan. Here I used select star, so naturally that meant I couldn't. But I can get an index-only scan even on Postgres 18, and I'm showing that here. Unfortunately, it's much slower. That's the problem. I didn't have to coerce the planner, by the way, it just did this on its own. So yeah, we're saving we're not getting any heap fetches, so in that sense, this is good. But now we're not pushing down the department keys to the index access method. Rather, those are evaluated as filter quals shown here outside of the B-Tree access method itself using expression evaluation. So on balance, that makes it much slower. So evidently, we cannot get the best of both worlds. One can imagine some kind of hybrid where, like the bitmap OR, we have 2 different index scans, each for the 2 distinct ranges plus the equals any, that guaranteed that no duplicates will be returned, that could, as before, be treated as one continuous index scan, thus making it safe to do order by limit and have the scan terminate early, making it safe to do index-only scan. So we want the best of both worlds, but evidently we're not getting it with this more complicated OR construct. The costing is not great here either, owing, I think, to the innate difficulty with costing a plan like this one. The statistics that are available are somewhat unreliable, so it's quite tricky to cost any index scan that's doing skipping for all kinds of reasons. Okay, so we would like to not have to have this false choice forced upon us, and by having this capability, we could conceivably avoid having to make a choice. It might still be true that a bitmap OR was the fastest plan, but probably we would want an index-only scan if we could potentially just have only those columns from the index in our select. If we could get away with that, it would be very nice to get an index-only scan. I'm not going to go into too much detail about it, but the MDAM paper describes a framework for rewriting. This is a very complicated OR-based predicate. It's using a similar table to the one I've been using in many of my examples. It's a mess, actually, to be honest with you. And they actually say in the paper, imagine this is like written by, it's machine generated. We can nevertheless, despite all the complexity, despite the fact that there is contradictory, the example I gave made it easy in the sense that I happened to pick up, my two ranges didn't have overlap in any way, so it was convenient for the purposes of the example. But what if they were somewhat overlapping? Then in order to not return TIDs, in order to make the scan correct, we would have had to have accounted for that. In no event can we allow the scan to return TIDs. It has to behave as if it was one continuous index scan, even if it's in reality a bunch of different index scans against the same index that are kind of pretending to just be one big one. The paper goes on to describe how the predicate I just showed you can be reduced to this series of accesses, numbered 1 through 11. This is in key space order, so obviously 2, in the case of the department, 2, 4, 5. It's in the same familiar order as the index itself, and thus allows us to maintain the illusion of one continuous index scan. So we took that very complicated predicate you saw on the previous slide, and through clever pre-processing, through clever analysis, reduced it to, took all the parts of the predicate and made it into this table of accesses that are in what's called a variant of disjunctive normal form. Now, notice that we still have some ORs here, 5 or 10. So it's not, strictly speaking, in disjunctive normal form, but this is the ideal thing that the B-tree code would want, because you could think of this as being like a scalar array op. It could be, you can imagine it being where item class in 5, 10, and so on. So this is the ideal form that the B-tree code would want to be passed these index scans in. I'm imagining this as being sort of like an append node. Perhaps some of you are familiar with how append nodes appear with partitioning. You could have an order by on the primary key for the partition table, order by limit, and that'll work. It'll show you an append node whose children are, there's going to be one child node for each of the index partition indexes. And what you would hope would happen with a query like that, where you've an order by limit, is that only the first or perhaps second of the index scan nodes would actually be executed. Explain analyze would hopefully show that such a query didn't need to execute more than the first node before it found sufficient rows to completely end the scan. Same principle here. So if you imagine a append node and each of these table entries is its own distinct index scan, each of which has its own operators. It's not that homogeneous. It's putting things in key space order, but there's different operators used for each distinct access. That's kind of the big picture of it. So there are many remaining questions as to how best to implement this. I'm sort of looking at this from a B-Tree point of view. That's where I'm most comfortable, but I'm trying to drum up interest in this area. Hopefully I'll get some of that. Somebody maybe can help me with this stuff. I'm considering working on it. I think there are certainly some cases where this additional capability with OR optimization would be super compelling. Maybe we can identify some subset of it that would work. I'm not sure. So help wanted. So some conclusions. I'm pretty much just summarizing the talk here. Skip scan works by treating a composite index, the familiar multi-column index B-trees that you all probably use already, treating it as a multidimensional structure. It works very well together with in-lists, with ranges, etc. At no point do more complicated examples kind of stop working because the predicate you put too much stuff in it. It's very, very good at finding the most efficient way to scan the index given the requirements dictated by the query. This is only possible if you're using an in-list. If you're using a simple OR list, in previous versions, you wouldn't be able to combine that with an array. You would invariably get one of those bitmap OR plans that we saw with all the attendant downsides. But now, thanks to work by other people in the optimizer, that's no longer true. And my hope is that this can be extended to more complicated cases involving arbitrarily complicated ORs with contradictory or redundant aspects to them, ultimately allowing the same basic trick to be performed that we've already seen simpler examples of, where there's a bunch of different index scans that are all pretending to be one continuous index scan, and thus preserving the index sort order, and thus allowing us to do index-only scans. So we'll see what happens. Watch this space, I guess. Any more questions?